Hello everyone, welcome back to Econ 704. And this is the second half after the midterm exam. You will notice several differences in the second half. First difference is that we're gonna use slides instead of handwriting most of the lectures. And the second difference is that we will no longer follow any textbook closely. You can see in our syllabus that I posted at the beginning of the semester that there are several books that can be useful for this part of the course, but I will not follow any of them very closely. If you want me to recommend one book to read, then you can read Stock and Watson. If you just want to read one book, then Stock and Watson is the book that you can read. So now let's get started. In the second half, we'll start the study of econometrics, and we will focus on linear models. And the first lecture will be an introduction to linear models. So first, let me start with the definition of econometrics. There are many different definitions of econometrics. Different economists, different econometricians would define the subject differently. But let's look at an authoritative figure, Ragnar Frisch, who was the person who invented the word econometrics, and see what he thought econometrics should be. So he wrote that econometrics is concerned with the task of developing and applying quantitative or statistical methods to the study and illustration of economic principles. So let me try to dissect what he said was. So econometrics is a task of developing and applying quantitative or statistical methods. So it's going to be quantitative and it's going to be statistical. It's going to require data. Although in the first lecture, we will not talk about data. And what's the purpose of this method? The purpose of the method is to study and elucidate economic principles. So basically, it is a quantitative statistical method for the study of economic principles. Let's start with economic principles. What are economic principles? Let me give you some examples. The law of demand is an economic principle. The law of demand says that when price increases, demand falls. This law of demand can be derived from consumer decisions. The rational choice of consumers lead to the law of demand. That is an economic principle that comes out of the consumer choice theory. The law of demand basically describes the relationship between demand and price, how demand should react when price increases. And another economic principle would be the law of incentives. In economics, we talk about incentives a lot. People respond to incentives. For example, does paying teacher to attend school increase their attendance rate? Well, in the United States, teachers attend school. That's not a big deal. But in some developing countries, teachers by default do not always attend schools. They're supposed to, but there is no mechanism there to ensure that they do attend schools. So there are some people who study how teachers respond to incentives when they decide whether to attend school or not. So that would be the law of incentives. Paying them to go to school, they will go to school. That's a relationship between the pay and the action of attending school. Economics are also concerned about institutions, not only price or incentives, but also institutions. For example, moving people out of poor neighborhood increases their welfare. So that's something that a lot of economists study as well. Moving people out of poor neighborhood can possibly increase employment opportunity or improve the environment that the children grow up in, and therefore increase their welfare. So these are all examples of economic principles. To give a summary of all of those, what are economic principles? Economic principles are about relationships between random variables. So the law of demand is about the relationship between price and demand. And the law of incentive is about the relationship between the incentive and the action. And in the problem of institution, the effect of institution, the economic principle is the relationship between the institution, for example, the neighborhood, and people's welfare or people's action. So these are all relationship between random variables. So economic principles are about random variables, which is why we spend half of the semester studying random variables, like the relationship between cats. So we want to study the relationship of random variables. How can we describe, how can we study the relationship between random variables? We have learned one way to describe the relationship between multiple random variables, which is joint distribution, or conditional distribution, which is a derivative of joint distribution, which is derived from joint distribution. Okay, so joint distribution is a way to describe random variables. It is a very comprehensive way to describe the relationship between random variables, because the joint distribution between random variables can describe the whole picture of how the variables are interacting. However, because it's so comprehensive, it is too complicated because it's a function. And if you have two variables, it's a two-dimensional function. If you have three variables, it's a three-dimensional function, and so on and so forth. Even in the two-dimensional case, a function is rather complicated. It's hard to imagine it in your mind. So joint distribution is very comprehensive, but it is complicated. We also have learned another way to describe relationship between random variables, which is correlation and covariance. Correlation or covariance. The advantage of correlation and covariance is that they're very simple. Covariance is just one number, and correlation is even simpler. It's a number between -1 and 1. However, the disadvantage of correlation is that it is only defined between two random variables, say x and y. What if you have a third random variable and you want to see how the three random variables interact among themselves? Then you can't do that with correlation. So correlation is simple, but it's limited. Well, joint distribution is very comprehensive, but it's too complicated. So to find a middle ground to that, we are going to use a linear model that I will describe a little later. And before doing that, I want to emphasize why we want to study the relationship among more than two random variables. Well, as I described, the law of demand is between a price and a demand, which is relationship between two random variables. The law of incentive is also between two random variables, the incentive and the action. And the effect of institution is usually also about two random variables, the institution and the outcome. So often the economic principle boils down to a relationship between two random variables. Can we just look at the correlation? Doesn't that tell us the story already? But the problem is that, as you may have heard in statistics course or somewhere else, correlation is not causation. So correlation doesn't really describe the causation. The correlation between a price and a quantity doesn't necessarily describe the response of demand to a price change. So correlation is not a causation. Often, to estimate a causal relationship, we need to get more variables involved. And getting more variables involved will help us to estimate a causal relationship and may also help in other ways as well. So we're going to talk about these things in future lectures. So these are the reason that just focusing on correlation is not enough. Just focusing on two variables is not enough. Just to maybe to beat the dead horse, give you a couple of examples to illustrate why correlation doesn't mean causation. For example, in mid-spring every year, many Christians withdraw from eating meat. So that's a tradition for 40 days. And this religious practice is called Lent. And the name for this practice is called Lent. During these 40 days of Lent, economists observe that the sales for canned tuna soars. So sales of canned tuna is the demand for canned tuna. The demand for canned tuna increases a lot during the Lent period. It is also found the average price for canned tuna falls during this period. If you let X denote the price of tuna and Y denote the demand of tuna, they seem to be negatively correlated. Is this the law of demand? Can you say that this correlation predicts how demand changes with tuna price? Can a firm who sells tuna use this correlation to set price, to maximize profit? Well, not necessarily. One complication is that in the period of Lent, people's demand for tuna increases regardless of price because Christians cannot eat meat and they want to look for meat alternatives like tuna. So that complicates the relationship. So the observed relationship is not necessarily the response of tuna demand to a change of price. And just to maybe make this a little bit even more confusing, consider another example. In some municipality, in some cities, the price for residential gas supply changes month to month. So the price for gas supply changes month to month, and it's generally higher in the winter months. So gas price is higher in winter months. And because gas is the primary heating source for many homes, the demand for gas also increases in winter months. So gas price is higher in winter. Gas demand is also higher in winter. So if you let X be gas usage and Y be gas price, they are typically positively correlated. Do you consider this a violation of the law of demand? Does the law of demand not hold for gas? Well, you might think maybe not necessarily, because in the winter, people's need for gas is higher, regardless of price. So how do we dissect these complications and actually identify the law of demand from these complications? That will require us to introduce more variables than just the main variables that we are interested in. So these are the reasons that we might want to involve more than 2 random variables and want to study more than correlations. So what is the point? The point is that we can use a simple model that will allow us to involve more variables, more than 2 variables. A simple way to describe the relationship between 2 or more random variables is through a linear regression equation. So a linear regression equation is the main focus of this course. So what is a linear regression equation? A linear regression equation relates a dependent variable y to some right-hand side variables, say x and z, in a linear way. So you write y as a linear function of the x and z variables plus u. So I'm going to explain these notations later on in more details, but just to give you a first impression of a linear regression equation is, that would be what a linear regression equation looks like. When you have one dependent variable and 2 variables that are called kind of the explanatory variables. And clearly, on the right-hand side, you're not limited to 1 or 2 random variables. You can add as many variables as you want. So it can easily accommodate many variables. So on the right-hand side, you can have, say, k explanatory variables. And the coefficients describe the relationship between y and these x variables. And the u term will capture anything in y that is not described in this linear function of x. And precisely what these coefficients and the errors mean will depend on, actually, the purpose of the model. So let me first define these quantities in more details. So this y is typically called the dependent variable. That's the variable, that's kind of the outcome that you're interested in. And the x variables are called explanatory variables, or sometimes it's called covariates, or explanatory variables, or covariates, or right-hand side variables. We use these different terms for the same things. And the u is called the error term. Now, these are the random variables. So all of these are random variables. And this linear equation relates these random variables, put these random variables together. And what about these betas? These betas, at least for now, these are non-random. And there is a beta 0 that's not multiplying any random variable, and that one is called the intercept. And there are the beta 1 to beta k's. These are called the slope coefficients. So beta 1 is the slope for x1. Beta 2 is the slope for x2, and beta k is the slope for xk. So the beta 1 to beta k are slope coefficients. Beta 0 is the intercept. So these are the names for the quantities involved in the linear regression equation. But now that we have their names, but what do they really mean? Just naming something doesn't give that thing a meaning, right? I can tell you I have something in my hand and I call that thing Bob. That doesn't tell you anything about what is in my hand, right? I just know the name of that thing is Bob. That's not useful, right? Well, the names will help us to talk about the thing, but it doesn't tell us what they really mean. In order to actually know what the linear regression equation really mean, what the quantities in them really mean, the linear regression equation needs to have a purpose. So the interpretation of the equation depends on the purpose of the equation, right? The purpose that we have in mind when we write down that equation. That will determine the interpretation for the quantities in that equation. And different purpose requires different sets of assumptions on the quantities, and the different purposes will determine what interpretation we can put on the different components of that equation. What are the main purposes for linear regression equations? What purposes do people usually have in mind when they write down linear regression equations? I summarize three main purposes for writing down the linear regression equation. The first purpose is to describe data. This we call the descriptive purpose. So descriptive say you just want to describe how the variables are related. And the second purpose is infer causality. So it's to infer what causes what. Usually it's what causes y. So which of the x variables causes y, and how does it affect y? How does change of x affects y? So that's infers causality. So the second purpose is to infer causality. So that's a causal purpose, descriptive purpose, causal purpose. And there is a third purpose of using the linear regression equation, which is to do forecasting. So you can write down a linear model and estimate the coefficients and use the linear function of x with the estimated coefficient on the right-hand side to forecast future values of y. So that's a different purpose, again, than the descriptive and the causal purpose. Once the linear regression equation has a purpose, once you decide what the purpose of your study is, you can then make the appropriate assumptions and then make your equation a model. So once you have the purpose, you make the right assumptions that's appropriate for your purpose, then your equation becomes a model. So what is a model? If you just write down the linear regression equation as we did on the previous page without telling me anything else, that is just an equation. That's just a mathematical equation that has a bunch of variables on the right-hand side and a random variable on the left-hand side. That's not a model. That doesn't mean anything. Only when you give the linear regression equation a purpose and then make appropriate assumptions about the random variables in make assumption about the components in that equation, only then you have a model for either the data or for the world that you're trying to describe or for the future world that you think would be. So let me start with descriptive model. We're going to start with descriptive model. We're going to start with the descriptive purpose. That is, suppose we just want to describe how the variables are related in the population. We want to describe how the variables are related in the population, and we use this linear regression equation when we want to describe how the variables are related in the population. What assumptions do we want to impose on the different components in the model? Now we need to make assumption about the error term u. We need to make assumption about the error term u. And the assumption about the error term u determines what kind of descriptive model we are talking about. There are different kinds of assumptions that we can put on the error term, and this will lead to different descriptive models. The first, maybe the most commonly referred to model is the conditional mean model. And we're going to focus on this one for now. So the conditional mean model, we'll talk about what assumption we need on the error term in order for this linear regression equation to be a conditional mean model. And the second kind of descriptive model, which is related to the conditional mean model, is the linear projection. This can be a linear projection model as well. For linear projection model, we make a different assumption about the error term, an assumption that's slightly weaker than the one required by conditional mean model. And yet another descriptive model would be the conditional median model or conditional quantile model. And for this, we will not talk about in this course. But basically, to give you an idea of what these are, the conditional mean model will make assumption about u so that this linear function is the conditional mean or conditional expectation of y given x1, x2 to xk. And the linear projection model will make assumption about u so that this linear function of x is the projection, linear projection of y on x1, x2 to xk. And the conditional median model will make assumption about u so that this linear function is the conditional median of y given the x variables. And similarly, the conditional quantile model will make assumption about u so that this linear function is a conditional quantile of y for some given quantile. And for today, we will focus on these two, and these two will be talked about maybe in future courses. Let's start with conditional mean. For conditional mean, the assumptions we make are that the error term is the difference between y and the conditional mean of y given x1 to xk. And that is not enough. We also need the conditional mean to be linear in x1 to xk. And this is a substantive assumption that could be violated. So you can consider this one, you can consider assumption 1 to be just a definition for the error term. You can think about it as an assumption, but it's really just a definition for the error term. It defines u to be the difference between y and the conditional mean of y given x1 to xk. And this second assumption is more substantive, meaning that it can be restrictive, can be violated in some populations. Now, if you have these two, let's say if you define u to be the difference between y and its conditional mean given x1 to xk, and if you assume the conditional mean is linear in x1 to xk, then this colorful equation that we wrote down is the conditional mean regression. And the observable part, which is the part that has only the x, not the u, so this is the observable part. That part describes the conditional mean of y given x1 to xk. Well, that is hardly surprising because u is defined to be y minus the conditional mean of y. Now, if you subtract u from y, then you get y minus u equals this linear thing. And that linear thing, according to this assumption 1, is equal to that conditional mean of y given x1 to xk. So it's not surprising at all. So from this linear equation, we know y minus u is beta 0 plus beta 1 x1 plus delta beta k xk. And that is equal to e of y x1 to xk. This is by assumption 1. So that is not surprising. When you make these two assumptions, this colorful equation is the conditional mean regression, in which the observable part describes the conditional mean of y given x1 to xk. And assumptions 1 and 2 also imply something else. It implies that the error term u is mean independent with the covariates. So in the first half of the semester, we learned about the concept of mean independence, which, remember, is an intermediate concept between zero correlation and full independence. So mean independence is defined to be conditional mean of u given the x are a constant. Here we normalize it to 0. So EU given x1 to xk now is 0, and it doesn't depend on x1 to xk, which is important, right? So 0 doesn't depend on x1 to xk. So therefore, the error is mean independent with the covariates. So how do we know that this is true for the conditional mean model? We can derive that from assumptions 1 and 2 that we made. So to derive that, we can write EU given x1 to xk equals E y minus beta 0 minus beta 1 x1 minus beta k xk given x1 to xk. Now, as we learned, so conditional expectation is just an expectation. Conditional expectation is still an expectation. An expectation is linear. So conditional expectation of this additive quantity is the conditional expectation of y given x1 to xk minus expected value of beta 0 plus beta 1 x1 plus beta k xk given x1 to xk. And we just derived that ey given x1 to xk equals is a linear function, and at equals, and according to the linear equation, that linear regression equation that we wrote down, this equals beta 0 plus beta 1 x1 plus beta k xk. And now, what is this conditional expectation? Given x1 to xk, given x1, x2 to xk, given all the random variables x, so given the value of all the covariates, this random variable's value is already given because this random variable is a function of the covariates. So given the value of the covariates, the value of this function is no longer random. If it's no longer random, then expectation of it equals itself. So therefore, that is also equal to beta 0 plus beta 1 x1 plus plus beta k xk. And that is clearly 0. So for the conditional mean model, the error term by definition is mean independent of x1 to xk's. If the conditional mean model assumptions, these two assumptions are satisfied, then the error term is automatically mean independent of the covariates. Just by definition, this holds. Okay, so that's the setup that you have for the conditional mean regression. So how do you interpret the quantities in this regression? How do you interpret U? U is by definition the difference between y and its conditional mean given x1 to xk. So that would be the interpretation of U. And what about the interpretation for this observable part? The observable part is the conditional mean of y given x. So therefore, if you plug in the values, little realization values, x1 to xk, then this quantity with the realizations plugged in is the average y value for individuals with x1 equals little x1, xk equals little xk. So for example, if x1, say is the gender dummy, is 1 if the person is female and 0 if the person is male, and say x2, let's say x2 is the dummy variable for college graduate. So that x2 equals 1 if the person is a college graduate and 0 otherwise. Then beta 0 plus beta 1, say times 1, which is a realization of x1, plus beta 2 times 0. 0 is a realization for x2, and 1 is also a realization, but let's say we take 0, the 0 this realization of this dummy variable. Then this is the average y value among the population, average y value or expected y value. Let's say expected y value for female non-college graduates. Right, so that's an example for interpreting this conditional mean model. Then what's the interpretation for each of the coefficients? The interpretation, say, for beta 1 would be the association between the 1 unit change of x1 and the change of y. So 1 unit higher of x1 is associated with, on average, beta 1 units higher of y if beta 1 is positive, or minus beta 1 units lower of y if beta 1 is negative, holding x2 to xk constants. Holding the other covariates constant. So in that example, in this example, continuing that example, beta 1 is the expected y difference between genders holding x2 constant, holding the college graduation status constant. Holding x2 constant, what is the average or expected y difference between genders? And that would be the interpretation for beta 1. Or in other words, in newspapers, you might see that a woman earns 87 cents of a dollar that a man earns. That would be, that 87 usually is just comes from a simple regression of y on x. That's the conditional mean of y given female minus conditional mean over the conditional mean given male. You could also hold education constant and see with among men and women with the same education level, what's their expected income difference? And that's described by beta 1 in a conditional mean model with 2 variables. Now let's consider a very simple example, a numerical example, see how you can use a linear model to describe the conditional mean. So here, let's start with a single binary x variable. X is class size, which takes only 2 values, 20 and 40. And let y be the pass rate of math test. Suppose that for students in classes of size 20, the pass rate is 90%. And for students in class size of 40, the pass rate is 80%. So EY given x equals 20 is 0.9, EY given x equals 40 is 0.8. Now, on this graph that contrasts the conditional mean of y given x and x, we can draw these 2 points. Say these 2 points are these 2 points here. So say that is 20, sorry, that is 40, and that is 0.8, and say that is 20, and this is 0.9. And there is always a line through these 2 points. You can draw that line, and you can compute the intercept and the slope of that line. So for this conditional mean relationship, conditional expectation relationship, the linear conditional mean model looks like this. So this is our beta 0, and this is the beta 1. Conditional mean of y given x in this case equals 1 minus 0.005x. Now, that is the simplest example possible, and you can always find a straight line through 2 points. So now suppose that the x can take more than 2 values. Okay, so this slide just says that u defined this way, you can write the model in terms of y equals this linear function of x plus u, and the u will necessarily satisfy this mean independence with x. Now suppose you have 3 points of values for x instead of 2. Let's say you add a class size that is 30, and let's say ey given x equals 30 is 0.85. And what is that point on the line? Well, I designed this point so that this line is on that straight line that we just draw. So this linear conditional mean model still describes this conditional mean. So it's still correct. The assumptions of the conditional mean model is still correct. And this linear equation is still the conditional mean model for y given x. But clearly, this third point doesn't need to be on this straight line that you got from the first 2 points. So it could be that that third point is not on that straight line. So you have 3 points now, but you do not have a straight line through the 3 points. You might have a curve, but it's not a linear function of x. So what do you put in here to make u satisfy the mean independence with x? And that is clearly not a linear function of x, but rather a nonlinear function of x. And mathematically, you can do that. People do study nonlinear regression equations, but in this course, we will not go into that. But instead, let me talk about a remedy to nonlinearity, and that doesn't involve nonlinear regression. Okay, this may be called a remedy, or maybe called something else, like a compromise. And that's treating linear regression equation not as a conditional mean model, but as a projection model. So when the conditional mean is not linear in the x variables, there isn't any value of the parameters that satisfy this equation. Clearly, right? If there is any parameter value that satisfies this equation, then the conditional mean would be linear. But if it's not linear, then there is no beta values that satisfy this equation. But then how do you define this colorful linear function to make it still meaningful in that linear regression equation? one way that people define these betas is to find the linear function of x that is closest to the conditional mean as possible, as close to the conditional mean function as possible. So you can find the coefficients that minimizes the expected square difference or mean squared error between the conditional mean and this linear approximating function. So this is not going to be equal to the conditional mean if the conditional mean is not linear, but we want to find a linear approximation that is as close as possible according to this squared expected difference. Expected squared difference. And the solution to this problem is called linear projection, or simply projection. And it is denoted by projection of y on x1 to xk. So that is the definition of linear projection. By definition, projection is linear, right? Because it is defined to be a linear function. So by definition, linear projection is linear projection of y on x1 to xk. So this should be xk. x1 to xk is a linear function of the x variables. And if you now assume the error term to be the difference between y minus the projection, then this colorful equation that we had is a projection regression. It's no longer a conditional mean regression, but it's now a projection regression. It is only a conditional mean regression when the conditional mean is linear, in which case projection coincides with conditional mean. In general, if the conditional mean is not linear, projection is not equal to conditional mean, but it's only an approximation of the conditional mean, then this colorful equation is a projection regression, is not a conditional mean model. By definition, the projection error, which is defined by this, the projection error term satisfies the orthogonality condition, which is described by this. So the correlation between the u and the x variables are zeros. So this condition is weaker, as we learned before in the first half of the course. This is weaker than mean independence of u on the x variables. Now let's try to derive these orthogonality equations that the u has to satisfy for the projection model. We're going to start with the definition of projection. By definition, these beta parameters in the projection model are the solution to this minimization problem, where we minimize the expectation of the squared difference between the conditional mean of y and this linear function. Since this is a square function, is a convex function, smooth convex function, we can use the first order condition to solve this problem. Let me write down all the first order conditions that the optimal solution should satisfy. So this is the first order condition with respect to B naught. Notice that I plugged in all the optimal values because the optimal values are the ones that makes this first order condition hold. And this is the first order condition with respect to B1. And this is the first order condition with respect to Bk. So you got k plus 1 equations for k plus 1 unknowns. Now, I'm not going to solve this equation, but instead, I'm going to define this difference between the conditional mean and the linear projection to be E2. And E2 is the approximation error of using the linear projection to approximate the conditional mean. So if you define that to be E2, then this is also E2. And that is also E2. So the first order conditions implies E2 satisfies the orthogonality condition. E2 has expectation 0. E2 has 0 correlation with any of the x variables. So we define that to be E2. Then this first order condition will imply the expectation of E2 equals 0, expectation of E2x1 equals 0, expectation of E2 times any of the x equals 0. So this is implied by the first order conditions. But E2 is not the error term. The error term instead equals y minus the projection. For the linear projection model, u equals y minus the projection, which equals y minus the conditional mean of y given x1 to xk plus the conditional mean of y given x1 to xk minus that linear projection. Notice that this is E2, right? So this is E2. And this difference, we can call that E1. So define that to be E1. So U is kind of decomposed into two parts. One is E1 and the other is E2. Now, what conditions does E1 satisfy? By definition, because E1 is the difference between y and its conditional mean given x1 to xk. So we have shown on the page where we showed the mean independence of the error term with the x for the conditional mean model. This difference is mean independent of the x variables. And not only mean independent, but also it has expectation 0. And from the first half of the course, we know mean independence implies 0 correlation. So if the conditional mean given the x variables equals 0, first of all, it's going to imply the unconditional mean equals 0, because by the law of iterated expectation, that equals expectation of the conditional mean, and that is expectation of 0, which is 0. And also, mean independence implies 0 correlation. So therefore, E1 times x1, which equals the covariance of E1 and x1. This equation is due to E1 equals 0. And the covariance equals 0 because mean independence implies 0 correlation. So that is because. So therefore, E1 has mean 0, E2 has mean 0, U is E1 plus E2, therefore U also has mean 0. E1 has 0 correlation with x1, E2 has a 0 correlation with x1, and U equals the sum of E1 and E2, therefore U also has 0 correlation with x1, and so on and so forth. So therefore, EU equals E1 plus E2 equals 0, and EX1U equals E1x1 plus E2x1 and equals EE1x1 plus EE2x1, and that equals 0, and so on and so forth. And we have shown that the error term in the projection model, in the linear projection model, automatically satisfy the orthogonality condition. So U is orthogonal to all the x variables by definition. Now, if you go back to the simple example we considered where x takes 3 values, we got 3 points on the space of EY given x. And these 3 points are not on a straight line, but you can draw a straight line that is kind of close to all 3 points in such a way that it minimizes the approximation error, the expected square of the approximation error. Then this straight line that you draw, that is the projection of y on x. And the error term in the linear projection model automatically satisfy these orthogonality conditions. So how do you interpret the projection model? We have talked about interpretation of the linear conditional mean model. Now, if the conditional mean is nonlinear, the linear regression equation cannot be interpreted as a conditional mean model, but instead it could be a linear projection model. But how do we give a precise and intuitive interpretation for the linear projection model? It is actually quite hard to do so. In practice, we simply view a linear projection model as an approximation for the conditional mean model and actually interpret it pretending that it's a conditional mean model, but in the back of our mind, we acknowledge that this is a projection to the conditional mean model. So in the next video, we'll talk about causal models.